And good eye, Caitlin. So, no. So we've already discussed the concentration of free enzyme and how it decreases initially, but you get it back. Now we're going to discuss the concentration of substrate. And so what happens to the free substrate as time goes by? Is it going to go up or go down? Go down. Do we ever get it back? No, not unless the reaction goes backwards. And so it's going to look something like this. Maybe it doesn't matter how steep. Maybe you make yours really steep. Okay. And now in this color, I'm going to draw the concentration of the Michaelis complex. What will at time 0, what will the concentration be of the Michaelis complex? 0, because the reaction hasn't happened yet. So that one's an easy one. We can just start it down here. And what's going to happen to it with time? It's going to go up. So there's going to be a little bit of a lag. And then it's going to go up. And then it's going to be steady, because it's at equilibrium with EP. And then at some point in time, it's going to go back down, because you're going to start to run out of things. It may not go exactly to 0. You know, in the perfect world it would, but it may not. And then I'm going to have to switch colors for your EP. Ooh, on this thing, I actually draw it much better than I do when I try to draw this on the board. For those who've had special topics class, we've already discussed something similar to this, if not this exact same thing. So what's going to be the initial concentration of EP at time 0? It's also 0. Is it going to, and it will have a lag, it's got to go up, but will its lag be shorter or longer than ES? Longer, because you got to make the ES first. So la 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 la, and then it goes up. It may be higher than the ES concentration, maybe lower. I'm just going to draw mine higher so that way we can see it better. And its plateau is going to stay a little bit longer because of the fact that, you know, you use up all the ES first, and then it's also going to go down to approach 0. And then last but not least, we have product. Which product, for those who hopefully are not colorblind, it's a different color. And what's its concentration going to be in the beginning?
0.
0, and it's going to be the longest one to make. So it's going to go, and then eventually it's going to end up somewhere. You know, maybe it's higher, maybe it's lower. I'm just drawing my higher so that way you can see it. Okay. We only have a couple of minutes left, but I just wanted to get everybody caught up for this. Let me go take a swig of my coffee. I feel like I'm on like Sesame Street, like near, far. Okay. Grover, you know, back in the day. And so we still have, I've got 2 minutes. Okay, so if we look at the, pardon?
Oh, Dr. Harris's Cookie Monster.
Yes, yes. So if we look at, there's a section where here, where the concentration of ES and the concentration of EP, both are not changing. Okay? So they called that the area where the concentration of the enzyme-bound intermediates aren't changing. That's called steady state. And that's going to make the math for the next class much, much easier. That's the steady state. Those are steady state kinetics. And the reason why is because what's the derivative of a straight line, a straight horizontal line? 0. Okay? And so that's going to make the math much, much simpler. And the reason why is because the change in y is 0. 0 divided by anything is going to be 0. And so before that's called pre-steady state. So this is called pre-steady state. And this doesn't have a name because it's completely unimportant and irrelevant. And so Next class I'm going to pick up right here because we talk a little bit about what you can get from pre-steady state versus steady state.
The steady state is
where the change in the enzyme-bound intermediate, so ES and EP in this example, are both 0. Like they're straight lines, flat lines. Okay, so I'll go ahead and I'll end class with prayer. Okay, so yes, I'm going to pick up right, like literally, it won't let me start back at 0 without, I guess, erasing all of it, so I don't want to have to do that. But just to review from the last class, is the fact that technically there are 3 types of kinetics. There's the steady state, which is where the enzyme-bound intermediates, the concentration of enzyme-bound intermediates is not changing. And so in the example I gave up above, it was ES and EP are the only enzyme-bound intermediates. The other items can be changing, but not those 2. And it's going to make the math in just a moment much more simple. But it's limited in what it can tell you mechanistically. It can tell you things about maybe the rate-limiting step, or it can give you an idea on the catalytic efficiency, but it doesn't tell you the information about every single thing. Whereas the pre-steady state, which is what happens beforehand, everything is changing. So that usually tells you so much information, it's difficult to differentiate one piece of information from another piece of information. And then, as I mentioned before, the stuff here at the end that doesn't have anything special about it. So the 2 of the types are pre-steady state kinetics and steady state kinetics. And in this class, we're only going to go over steady state kinetics. There's a 3rd type of kinetics called single turnover, which it only tells you information about the rate limiting step under those conditions. But it gets used a lot whenever you're finding out the mechanisms of certain things. And so just in case if you're reading your papers and they talk about single turnover kinetics, that literally means that it's under conditions where there's so much enzyme that the reaction can only occur one time. So usually, unless binding is rate limiting, usually it gives you information about the chemical stuff. Okay. All right, so now what we're going to do is we're going to actually start talking about steady state kinetics and deriving steady state kinetics. So I'm going to try to do this without skipping any steps. And some of you who've had me in other classes, you may have seen this, but the more you hear it, hopefully the more likely it will be that it sinks in. And so, steady state kinetics. Steady state. Okay. And so here we're going to first talk about some assumptions that we can make about the steady state kinetics, and we're even going to do this, solve this for the simplest, the absolute simplest of enzyme mechanisms. Okay, so the simplest enzyme mechanism that you could have would be this, is where you have an enzyme, obviously, and a substrate, and it combines to form the Michaelis complex. And then it just goes on to release product. And this does explain certain types of reactions in vivo. Now, each arrow can be described by a kinetic rate constant. Remember, those are lowercase k's. And so what's going to happen here is if it goes in the forward direction, it gets a positive subscript. So that's K1. If it goes in the backwards direction, it's given a negative subscript, so K minus 1. And so that's how they differentiate. If it's K minus 1, that means it's just that first step going in reverse. Here we're going to have K2, and we're assuming that there's no K minus 2, or that K2 is so much greater than K minus 2 that it's negligible. Which, if you're doing initial velocities anyway, there would be no K minus 2 since you're not starting with a product. You don't have to worry about it going backwards. Okay, so we're going to have a couple of assumptions, which I've already stated one. One assumption is that the initial concentration of product, P naught, is equal to 0. So therefore, we don't have to worry about the K minus 2. This is going to be equal to 0 as well. So it's not going to go backwards. Because that does make the math more difficult. And the second one that we're going to make is called steady state assumption. That's where it gets its name for steady state kinetics. I have to be careful not to abbreviate that just right. Whoops. My hand hit that. So steady state assumption. And remember, that's the change of the enzyme bound intermediates, change in the concentration of enzyme bound intermediates is 0. It's not changing. Well, we only have one enzyme bound intermediate here, and so that means that the change of ES concentration with respect to time is equal to 0. So since derivatives kind of freak some people out, if you really wanted to, you could put triangles there, but it means the same thing. And another way to think that is that the rate of formation has to equal the rate of breakdown. Okay, because that must be true. Rate of forming has to equal, let's find the equal sign. Oh, they're back to playing that little ditty on the piano again. This has to equal the rate of breakdown. I'm just going to put break. Pardon?
Recording their new pop hit.
Mm-hmm.
Just be the same tune over again.
Same 3 or 4 measures. All right. Give everybody a moment to get caught up because I'm going to have to get to another screen in just a moment. But that's the important thing here. Once again, these are our assumptions. The change of the concentration of ES is 0. And so that means that as quickly as you make it, it equals the same rate as it breaks down. Okay, so that way, if one's coming along, one's breaking. One's coming, one's breaking. And so now what we're going to have to do is start to incorporate this into what we know for rate laws. Okay. So we know that the overall rate law for that reaction, it always has to start with a V. So, and we were doing initial velocity, so V naught. There always must be a K. Now, I've had to erase mine, but if you look at your notes where you've been writing, what K describes the formation of product? The formation of product. It's K2. And that's the only K. That's the only way to make product. Okay? And then that K2, remember rate laws are always rate is equal to a little k times the concentration of everything that's a substrate for that, or that's a reactant. So what reactant or reactants do we have in that reaction that uses K2? It's only the Michaelis concentration. Okay? So that's the rate law. But this is the problem. The problem is we don't know what the concentration of ES is at any one point in time usually. Usually, you know how much enzyme you start off with. You may even know how much substrate you start off with. Or even if you don't know how much enzyme you start off with, you know how much substrate that you're putting into it. And you can presumably know how much product you're making, because otherwise there's no way for you to measure velocity if you can't see your product somehow, or measure how much product you have. And so we have to put that in terms of things that we do know. So that's just ES. You can just think of it as like X from algebra. You know, it's an unknown entity that we have to figure out. So one thing is that the total concentration of E, which I'm going to call ET, at any one time has to equal the concentration in I apologize, but my brackets will start looking more and more like parentheses just because it's quicker and easier for me to write. But a parenthesis is the same, it means concentration. So it's going to be the concentration of free enzyme and the concentration of the Michaelis complex. Okay, so that must be true. All the enzyme that you have at that one time has to be either free or bound to substrate, because there is no EP complex. So we want to put everything in terms of ES, since that's what's in the V naught, in our equation here. Since this has an ES in it, we have to put everything in terms of ES. So let's define free E. So the concentration of free enzyme has to equal ET, concentration, minus the concentration of ES. Okay, so now we go back to that steady state. I'm going to change colors so it'd be easier to see. The steady state assumption, which was the formation of the ways to make ES, has to equal the ways to break it down. Okay? And so what ways do we have to form ES? You can go by K1, so it's going to be equal to K1, and then what concentration or concentrations is it dependent on?
E plus S?
Well, it's not E plus S, but
Just S.
because what if it was just A plus B going to form a product, what would be the rate law for that? It'd be K times the concentration of A times concentration of B. Instead of A's and B's, we just have E's and S's. Okay, so the way you form it has to equal K1 times E times S. So now, what way or ways can we break ES? What's one way that we can break it? Use it up. Look back on your, because I unfortunately had to.
K2.
It's K2. And K2 times what? ES, right? Because that's going on to form product. Is there another way to break it? Yeah, so that's where we put the plus. What other way can we break it down?
K minus 1.
Yep, the K negative 1, and it's dependent upon the concentration of. And so here, I'm going to redraw that. Let me change colors. Remember, this is what it looked like. It was E plus S. Going to form ES. Going to form E plus B. Whoops, that's not, it's supposed to be an R. It's supposed to be P. P. Okay, and so if we, and I really wish there was a way that I could block this. We've already done the K2 way. So one way to break ES is to go, quote unquote, forward. And so the other way to break it is to go backwards. And so that's where the K minus 1 comes in, because that's the rate. But whenever it's breaking down, what's the substrate for whenever it breaks down? Or what? Whoa, that was freaky. What is the concentration dependent upon to go backwards? What's the reactant for the backwards reaction? It's also ES. And so that's all that goes down here. And so that's why and I really wish I could cover this up. Well, I guess, let me put, because what I'm saying is, let's see if it'll let me put a box in. Come on now. Oh, it will. So if we hid that side, there's only one way to break it down. And the way to break it down is to go this direction. And when you're going this direction, this is the rate constant, and that's the only concentration. That's the only reactant there is to go backwards. So that's why I meant that, you know, you can literally just break it down either that way, or you can move it and break it down this way. And it's additive. I forgot the 2 on that one. 2. Okay. All right. So now we can actually, since the steady state concentration, steady state assumption, I'm sorry, says that the rate of formation has to equal the rate of breakdown, it must be true that this equals that. Okay. So now we just put those two reactions, what is that, the transitive property? I can't remember. I always mean to look it up, but you know, if A equals B and B equals C, therefore A must equal C. It's that property for those who are math minors. Perhaps you know. And so I'm going to go ahead and have to write that on a different slide. Okay, so we have the rate of formation, K1 E times S, has to equal the rate of breakdown, which is K minus 1 ES plus K2 ES. Now we can actually go ahead and look back, because what we can also do here is substitute in for this free E, because we don't know what free E is and we don't know what free ES is. And if you think back to like just algebra, you know, it's better if you can put everything in terms of one unknown than have two unknowns. And so we can substitute the equation for E in right here. I'm also going to go ahead and just combine these two terms so that way we don't have to keep writing it out over and over and over again. And so if we go back, and if you look back in your notes, remember free E was equal to what? It was ET minus ES. Okay, so we can then substitute that in. I'll change colors so that way it's easier to follow along. So then we would have K1 times concentration of ET minus ES times S is equal to, I'm going to factor out an ES here, and it's just K minus 1 plus K2. Give everybody a moment to get caught up. Need a swig of my coffee. So I got to listen to my Grover impersonation whenever I was uploading the last lecture onto YouTube. Acoustically, it was great, that whole near far thing. Okay, now I'm just going to multiply this all out. Well, not all out. I'm going to leave the right-hand side alone. And so we have a, let me switch colors where you can clearly tell one line from the other. We have a K1 times S, because see, that's true. There's a K here, K1 here, and an S here, and they're both being multiplied to the stuff that's on the inside of the parentheses. Times the concentration of ET minus K1 times S times the concentration of ES. And that's going to be equal to everything from the above. ES times, whoa, that's not an S, that's a 3. ES times this K minus 1 plus K2. So now if you remember from algebra, we have, let's just review, we know S, we know the total enzyme concentration usually. We just don't know ES. And so if you just think of this as algebra's X, these are all, constants or numbers that you know. So that's just a number. And that's an X. And we have an X on this side times a number. What you do is you combine your X's. You put them all on one side. So all we're going to do is add this big term here over to the right-hand side. So let's add that to both sides. So that way we get, and I'll switch colors again. We have K1 times S times ET is equal to K1 S ES plus ES times K minus 1 plus K2. So do we have anything in common that we can combine here? Or a common factor that you can factor out? Yes. Yes. Yeah. Yeah. That was odd. Okay. So K1 S, the left-hand side stays the same. ET is equal to, I pull out an ES, and I get this, weird-looking term here. K1 times S plus K minus 1 plus K2. So now let's just think about the mathematical logic behind this. The whole goal of this was to find the overall rate. Okay, that big V naught all the way back in the beginning of your notes for today. That big V naught was equal to K2 times ES. We can now solve for ES.
No.
Perhaps we will not be able to solve for ES. Okay, so now we can solve for ES. And I even remember to hit record again. So to solve for ES, we just need to divide both sides by the big thing in the square brackets. Okay, so it's gonna not look pretty. Let's see if I can somehow. Oh, it will. That is awesome. It's the little things in life. Take joy where you can. It's
Faith integration.
Pseudo faith integration, more like a Eastern religion kind of faith integration. They didn't say it had B. Okay, but that way I can still look at that. Look at all this. So I'm going to use it in this color. But yeah, I'm just going to divide everything by this big term. Okay, so we're going to have K1 times S times ET divided by K1 times S plus this entity of K minus 1 plus K2. And all that's equal to the concentration of ES. And we're going to do something here that's a little odd. I know it's hard to believe. But we're going to divide, we're going to simplify the big thing on the left-hand side by dividing out, factoring out K1. even though all three terms don't have a K1, there's a way to do that. And so what you do is it turns it into the following. Let me just rotate it. I wonder if it's going to keep on letting me rotate up indefinitely. But we're going to factor out the K1. So we have a K1 here, so this is going to cancel out, and a K1 here is going to cancel out. So we just have to divide the stuff in the parentheses by K1. And so that means we have the concentration of substrate times the total enzyme concentration is equal to the concentration of substrate plus, and remember, the little k's are constants. We just don't know what those numbers are, but they are a number. They don't change. So it's k minus 1 plus k2 divided by k1. And all that is equal to ES. Everybody, oh, and close bracket. I'll give everybody a moment to get caught up in the writing part so we can then talk about the implications, because right now that looks ugly. But it's going to turn to a beautiful thing. One thing I wanted to let you know is it's a real pain to upload each individual video to MyFire. And so what I've done is on the blog, I've created another page on the blog where it's just, it's pretty obvious. It says Biochem Lectures. You click on it, and I've got it according to chapter. And so all of them, I try to put them in the order of the chapters, and it includes the one that's missing for Mike Hershey. No, for everybody, the end of chapter 5 video is up there now.
Oh, cool.
Yeah, where I go over molecular motors and what's the other one? Molecular motors and it slipped my mind what the other thing was.
Muscle contraction.
That's a molecular motor.
Oh, immunoglobulins.
Yes, complementarity there. Okay, so we have this big term. Let's see if it'll let me. Oh yeah. But if you go all the way back in the beginning, we wanted to find this out. We had V naught, because that's the important thing, the reaction velocity, how fast is the reaction occurring, how much product is being made as a function of time, is equal to K2 times ES. So that means it's just K2 times that big thing. Okay, so I'm just going to rewrite it. I'm going to move the ET over just for simplicity's sake in just a moment. But it's the same thing. Divided by concentration of substrate plus K minus 1 plus K2 divided by K1. So that right there is the important equation. And this is where it comes from. Just by looking at it, if you try to plot this on a graph where y was your velocity and your x-axis was substrate, does anyone know what shape it would look like? I kind of doubt you would, but it actually comes out to a hyperbolic kind of relationship. Okay, and so they give these special names. You more likely you see it looking like this, written this way, where it's still V. I'm just not going to rewrite it as a V. Is equal to K cat times E. They just don't tell you that it's E total times S divided by S plus a capital Km. Okay, and that capital Km is called the Michaelis constant. And many times it's erroneously labeled as being the dissociation constant. The only time that Km is equal to Kd for substrate is in this example right here. If you have an EP, then it can't. It'll give you a lower limit for it, but it's not exactly equal to Kd. All right. And so this, what's this equation called? Does anyone know? This equation right here, where V is equal to K cat times E times S divided by S plus Km or Km plus S. It is sometimes written the other way. That's the Michaelis-Menten equation. That's something you should know. Okay, so now we're going to do limits. Oh, two different things. Awesome. Let's just see if I can. We're going to do limits.
So that's E total?
Yeah, that would be E total. It's just a lot of times you just say K cat times E times S. But that E is the total concentration of all the E's. Okay. All right, so we're going to just talk about what happens when substrate gets really, really big. So under conditions, so if the concentration of substrate is large, so that's where it's much, much, much greater than Km. So, which I mean, that's technically for those who are math sticklers, we're talking about the limit as the concentration of S approaches affinity. So what happens there is we're still going to have, obviously, V. It's still going to be equal to K cat times E times S. Because all the stuff on the top is still the same. But what does the bottom start to look like? If S starts getting bigger and bigger and bigger, to where, if you think about, let's say that S, I'm going to make up a number, is 1,000,000 and Km is 1. There's really not a big difference between 1,000,000 and 1 and 1,000,000. So what does, as that limit, as S approaches infinity, what does that bottom start to look like? Just S. Well, we have an S now on the bottom and an S on the top, and they cancel out. So therefore, this simplifies. So the limit as S approaches infinity is that V naught is equal to K cat times the total concentration of enzyme. And so it no longer even matters how much substrate is around. It's a zero order reaction. So it'd be a straight line, a flat line. Okay? And the way to think about this logically is you have so much substrate around that all of the binding sites and all the enzymes are completely used up. Okay, there's no more places for you to put another single substrate in there. And so that's why, and they give this a special name. Does anyone know or remember what this name is called? It's the maximum velocities, Vmax. You can never get faster than Vmax for an enzyme. So that's all equal to Vmax. So sometimes if you're reading a paper, it'll only tell you about Vmax. If you don't know what the total enzyme concentration is, you can only find Vmax. You can still find Vmax, you just don't know the exact concentration of the enzyme. This happens a lot in vivo, like inside your cell. Like how much exactly of hexokinase does a hepatocyte cell have? Well, it's kind of hard to tell. But you can tell how quickly it turns over and makes glucose 6-phosphate. Okay. And so you could find Vmax, you just couldn't find Kcat. Kcat is the upper limit for all of the first order rate constants, mathematically speaking. Okay. So that's if S gets really, really big. First of all, so you'll have to go back to look at, here. What happens when S gets really small? The limit on the other side. So as S approaches 0. Exactly. So if S approaches 0, or for those who don't like to think in limits, is really, 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 really tiny. So it's much, much less than Km. Then the concentration of S plus Km is approximately equal to Km. And so that would make it, the reaction, say V is equal to kcat times E times S divided by Km. And they usually just write it as kcat over Km. Or you could also see it written sometimes as Vmax. Because remember, Vmax is the same thing as kcat times E. So Vmax times S over Km. That's the same thing. So now if you plot this, where your y-axis is your velocity, your x-axis is your S, it just forms a line with the slope of Vmax of E over Km. Okay, so if we put all of this together, so I'll give you a moment to get caught up. I'm writing. We're going to see that what it looks like, it's going to be hyperbolic, a hyperbolic graph, assuming it follows Michaelis-Menten kinetics. That's why it's sigmoidal if there's cooperativity, and it changes this equation. Okay, so, whoops. So what this means, now I'm going to draw the actual graph. We have velocity here, which is, remember, the formation of products is a function of time, as a concentration of substrate. We know, well, at 0, it's going to be 0. Or it should be, let me change colors, is 0. And it's linear in the beginning. Linear. But then it's going to approach and become a horizontal line. Okay, so it's a hyperbolic. So on this graph, whoops, wrong one. This asymptote that this approaches, whoops, I didn't do a very good job of drawing it in straight line, but it's supposed to be a straight line. That's equal to Vmax, right? Because it keeps approaching as S goes to infinity. So that's where your Vmax, which remember Vmax is equal to kcat times E. So if you know your enzyme concentration, you can find the actual kcat. Otherwise, you'll find Vmax. So that's Vmax. So I really need to see if I can change and put that bar on the other side because my left hand keeps hitting it. So that's Vmax. We also know, let me change colors here, that the slope of the initial, the slope, mathematically speaking, is called the slope of the tangent as it approaches 0. But if you just want to look at it right here, this right here, as it goes up, that line, sound effects optional. Here, let me erase that because I'm going to put in a real arrow. That line, now that's an arrow. The slope of that line right there is your Vmax over Km, or your kcat times E over Km. Okay, so the slope, M, is equal to Vmax over Km. The reason why I wanted to point those out, because qualitatively now I'm going to, oh, and there's one other thing here that I want to point out before you go, is that if you go to the concentration, if you go to the halfway point on the y-axis, so you're at half Vmax, then you go all the way over till it hits the line of your function, and you go down to substrate. This point right there, I didn't put the big arrow in just because of time, that concentration is equal to Km. So Km, technically speaking, Km is the substrate concentration when you hit half of Vmax. Mathematically, you can stick that in to the Michaelis-Menten equation. You'll have Km plus Km on the bottom, so it's going to be equal to 2 Km. And so you're going to find out mathematically that that is true. And so the reason why I wanted to point these out quickly is the fact that, once again, this is as fast as the enzyme can ever be. This Vmax over Km, or Kcat over Km, is also called the specificity constant, or the catalytic efficiency. And I'm going to explain the next class what that means. And we actually have a little assignment that you guys do. And why that's important. Because for some things, that's the most important thing. Others is Vmax. Km is just a way to compare the relative affinities for an enzyme for two different substrates, or the relative affinities for a substrate for two different enzymes. It's kind of like a barometer. Because, you know, if you go well below Km, you're under these conditions. If you go well above Km, you're under those conditions. It doesn't actually have a lot of other importance. Okay. So right now I'm going to go ahead. Okay, that brings us to. So we're going to pick up right here. The next two slides are ones that just skip steps to solve the Michaelis-Menten equation, so I'm not going to go into any great detail here, other than just to review on what we did already. And this was for the simplest mechanism, which was just one that has binding and catalysis. And the reason one thing I don't believe that I had gone over was what the implications were for Kcat over Km, and Km in particular. But this just shows how we already went over the steady state approximation. We use this in order to ultimately solve and derive the Michaelis-Menten equation. Okay, and so we have this Michaelis-Menten equation here, and which is abbreviated as V initial, or V naught. That really does not come up very well. Here, let's move this out of the way. So it's V naught is equal to Kcat times the total enzyme concentration times substrate over Km plus substrate. And we went over like what happens whenever substrate gets really large or substrate is really small. So those were the two limits and what that looked like on that plot. Now, in the example that we did and we derived last time, you'll have to look back in your notes, but remember we had it to where it looked like the Kcat for that particular mechanism was equal to K2. And Km for that particular mechanism was equal to I have to look at someone's notes so I make sure I get the right number on the top and the bottom. What is who's the notes at?
Which notes?
The notes from the last class.
These are notes.
With all the little K's. One, because it's like K. I don't want to make sure I get them.
K1, K2? Little K's, right?
Right, but I mean, where when we had solved it here, then it should be.
Oh, I have that in my mind. I have it all divided.
Yeah. So that way, I just want to make sure I get the right numbers on the K's. Yes, K minus 1, K2. All right. It was equal to K minus 1 minus 1 plus K2 over K1. Okay, and I just wanted to point this out because of the fact that it's okay. Remember, these are all just constants, so these are numbers. It could be like 3 plus 2, over 4 or something. Usually it's going to be ridiculously large or ridiculously small numbers. But Km, the units for Km are always substrate units because when we drew out the function, V is going to be the y-axis and substrate is going to be the x-axis. It's hyperbolic. And if you don't know the exact enzyme concentration, you can only find what's called Vmax. Okay, so the Vmax here, let me just do a different color, is this asymptote that it approaches. And so it's going to have velocity units, which makes sense, which are going to be like molar per second or milligrams per milliliter per second or something like that. And I won't draw it in just for clarity's sake, but the slope right here was going to be equal to Vmax over Km. But I will say, if you go to 1/2 Vmax, you go over to wherever it hits the function, and then you go down, that is your Km. So Km will always have the same units as whatever your x-axis is. Because by default, it is the amount of substrate that is necessary in order to get to 1/2 of Vmax. And it's really just a barometer for the basic affinity for a substrate and an enzyme interacting with each other. Okay? Now I say all this because I'm going to have a take-home assignment that people in medchem I think already did. I know I always have them do it in enzymology, just to help explain this, because it uses an everyday metaphor in order to kind of get an idea of what Vmax really means, because it's the as fast as you can go, and what Vmax over Km mean, because that's the specificity constant, or it's also known as the catalytic efficiency constant. So it's usually the one that tells you how efficient your enzyme is with that substrate. Vmax doesn't, because just because it can go fast doesn't mean it's really efficient. It can be sloppy, so to speak. Okay. All right. So I do want you to be able to explain what kcat, km, kcat over km mean, and what Vmax is with respect to that. Vmax is kcat times E, because a lot of times in vivo you don't know the exact enzyme concentration. Like you don't know the exact, methyltransferase concentration right now in this, in your nerve cell. However, you could possibly be able to set up an assay to where you can measure the amount of product being formed. So product is a function of time. So you can get a velocity, so you can get a Vmax, but you just couldn't get the exact kcat because you don't know that exact enzyme concentration. All right. So now I'm actually going to work through this one with you, because nowadays a lot of times they use computers can do fitting to hyperbolic functions really easily, but especially in the old days they didn't. They liked everything to be a line. And so I don't know if you knew this or had learned it in math, in, I don't know, calculus or whatever study it is, but you can take a hyperbola, I'm just going to call this y and x, and you can transform it into a line by doing what's called a double reciprocal. So if you plot 1 over y as a function of 1 over x, it actually takes a hyperbola and turns it into a straight line. Okay. And so they used to always try to make linear, they would try to linearize the data. And so they would linearize Michaelis-Menten, and there's actually 2 or 3 different ways. One's called the Eadie-Hofstee, but the most famous is called Lineweaver-Burke. And what they do here is, if we just take our V is equal to, now I'm just going to say Vmax times S, because it's easier to write, Km plus S. Now we're just going to flip it over. So we have 1 over V is equal to Km plus S over Vmax times S. And then according to, I don't know if that's the law of fractions or what have you, but you can simplify this out to where we have Km over everything on the bottom, Vmax times S, plus S over Vmax times S. I'll give you a moment to get caught up. Because if you just look at that, you may not realize that that's a line. But now I'm just going to rewrite it. 1 over V, that's your y-axis, is equal to, remember the x-axis is 1 over S. So that factors out of this right here to give you Km over Vmax plus, how does this simplify, the second term? The S is just cancel out. So it's plus 1 over Vmax. Let's see if I can... Oh, awesome. The reason why we do that is because now, when you plot this, you're going to get this kind of a graph. Okay, and the y-intercept is going to be equal to what? What would the y-intercept be equal to if that was your, if that is your linear function? See, people get lost in the fact that there just seems to be lots of letters, but remember, it's just what's the definition of a line? Y is equal to mx plus b, and so therefore, what's going to be the y-intercept here? It's 1 over Vmax. What's going to be the slope? It's Km over Vmax, which is the inverse of the catalytic function. Catalytic function is Vmax over Km. I should say catalytic efficiency, not catalytic function. Okay, and if you solved for it, then you would find out that this is negative 1 over Km. Right here is the for the x-intercept.
So
Okay.
the catalytic efficiency is Vmax over Km?
Vmax over Km, yes. It's also called the specificity constant. Okay. And so that's why this is a Lineweaver-Burke plot. And one of the reasons why you just don't always use this one is, I don't know how much detail they go into in statistics, but the more that you manipulate the data, of course, the higher the error. And by doing double reciprocals, it does increase your error, typically. Okay, so that's why it's better to do a global fit, the hyperbolic fit. But sometimes, you know, it's just easier to see things using a line, but it does usually have a higher degree of error. All right, and this is what it's saying. This is just the words of what I said. It's called the double reciprocal plot. And the Burke here is not like little JC. There's no terminal E. It's Lineweaver-Burke.
Terminal E.
That is correct.
No relation.
No relation. So, okay.
There is a Burke that is the prominent biochemist in the paper, the enzyme I'm working on. Also no relation, but
Okay. All right. All right. So another K-cat is also called the turnover number because that is the fastest that it gives you the limit, the fastest that the enzyme can turn over one product per binding site per unit time. Usually we're talking about per second. And so if it was 10 per second, that means it's as fast as it could go. 10 times per second, it will make a product per binding site. Okay? Which a lot of our enzymes we're talking about only has one binding site. But there are some that can do multiple things at once. And Vmax is related to that because it's just going to be Vmax is equal to Kcat times E. And Km technically is the dissociation constant for all enzyme-bound species. And so that's why it doesn't always equal Kd, but it's just a good barometer to kind of get an idea. The lower the Km, the tighter the affinity, the tighter it's bound. Okay, so a high Km is not bound very tight. So, okay. And like I said, I'll have like a take-home assignment. I'll try to do it sometime later this week, and it'll give you plenty of time to graph it and play around and to look at like what it means. How can something be calorically efficient but not very fast? How can something be fast and not calorically efficient? Or how can it be both, fast and calorically efficient? This is just some of the examples here for the turnover number and the KMs, and then literally to find the specificity constant, you could just take KCAT and divide it by KM. They did not put the units though, which would have been really nice if they would have put the units on there. But you can see that some of these are quite fast and very specific, to where if you take 4 times 10 to the power 7 and divide that by 25, whatever the units are, which chances are that those units I would think are going to be micromolar. They may be millimolar, but you're going to get a very large number. And so, whereas if you look at it versus chymotrypsin, which chymotrypsin isn't nearly as catalytically efficient because it's 190 divided by 0.66. And so I would expect you just to be able to look at two sets of numbers like that and say which one would be more calorically efficient. Or you can even look at the same enzyme and they can have different efficiencies for different substrates. So they can have their main substrate and then have a different substrate under other conditions. Okay. All right, but what happens if you have more than one substrate? Then we actually have multiple ways that you can go about doing this. One could just be, and ternary just means that when all 3 things are together. So if we just have substrate 1 and substrate 2, and it doesn't matter which order that they bind, it usually matters what direction, then it's just called random. So it could bind substrate 1 first or substrate 2 first, then it makes the ternary complex ultimately to make, the product or products. Or for some enzymes it's ordered. It must bind substrate 1 first, then usually a conformational change would make it to where substrate 2 could then bind, ultimately then to go on to make the product or products. However, there's a third kind. It's called a ping pong mechanism, and it's also called double displacement, but most everyone just refers to it as ping pong, and it's because you never have a ternary complex. What happens is the substrate binds to the enzyme, then it usually modifies the enzyme by having a covalent intermediate, but it forms one product. That product leaves, and then this modified enzyme then comes in contact with a second substrate, and then you get your original enzyme back and the product, the second product. This happens a lot with transferases. So just to give a little cartoony way of showing it, whoops. Let's say that we have an aminotransferase, and I'm not going to go through, it's a mechanism that you're actually going to learn, I think it's next semester, but it's got an important lysine. The enzyme has a lysine on it, which I'm going to draw as a K since that's the lysine's, 1-letter code, and it binds the substrate. So, and the substrate's going to have an amino group on it. So that's S1. Then, and it's reversible by the way, what happens is the enzyme's lysine forms it's called a Schiff base, but it takes the nitrogen. And so the product that you're left with is substrate 1, whoops, it's no longer a substrate, it's now a product. It's product number 1, and it's now a carboxylic acid. Not a carboxylic acid, I'm sorry, it's now a ketone. Okay, so it now has a carbonyl group where it used to have an amino group. Then what happens is the next substrate comes in and binds to the enzyme. So, oops, let me put that in a different color. So this would be substrate number 2 comes, and it's got the ketone. And what happens here, which I'm going to have to put it, is you get the second product, which now has the amino acid. So what had been substrate 2 now gets the amino group, and you got your enzyme back with just its free lysine. So that's why it's called the ping pong mechanism, because you first bind one substrate. Usually it will modify the enzyme and then it will leave, so it transferred its functional group over to the enzyme to leave. Then the second substrate comes in, would take the amino group here in that instance to regenerate the enzyme and to make your second product. So that's why it's called double displacement, because two things are displaced, or ping pong, because it goes back and forth, back and forth.
I have a question about specificity.
Mm-hmm.
So you said it's Vmax over Km, so it can also be Kcat over Km? Does it give you the catalytic efficiency?
Right. Well, because Vmax and Kcat are related.
So why does the enzyme concentration not matter? Well, because it's per enzyme.
Well, I mean, the best units to use are Kcat over Km, but most of the time you don't know the exact concentration of enzyme, especially in vivo. And so then they use Vmax over Km as the catalytic efficiency. You can still use it as to gauge the specificity for one substrate over another, or for one enzyme over another for the same substrate. But if you know the enzyme concentration, like in vitro, then they usually prefer to use Kcat or Km. Okay. So then there we have different types of inhibitors. Reversible inhibition. So therefore, that's something that can bind, but it can be released, so it's not permanent. And for those, there are 4 types. There are 3 individual types and one that's mixed. Okay, and we're going to go over each of these in just a moment. And then, of course, we have the suicide inhibitors. The suicide ones are irreversible. Okay, so they bind. Usually it's covalent. And then that enzyme is dead. That's why it's called a suicide or irreversible inhibitor. And in the past, for the MCAT, they always include the competitive, because that happens a lot, and it's the easiest one to explain, by the way. But some years they included non-competitive in their list, some years they included uncompetitive, and some years they include both. We go over both. In reality, a lot of times in vivo, we're going to have more of a mixed situation, or where under certain circumstances it's primarily competitive or something like that versus non-competitive. Okay, but just in broad generalities, we have a competitive inhibitor is going to be binding to the active site, so therefore it competes with substrate, or it can actually bind to some other site that prohibits the substrate from binding. Okay? But usually we're talking about it binding to the active site. Non-competitive means it's going to bind someplace else, and it inhibits the enzyme where it's no longer catalytically active. Okay? But it doesn't necessarily compete with the substrate. And then uncompetitive binds to the ES complex, so it doesn't compete at all with the substrate. It recognizes the Michaelis complex, and the mixed is just a mixture. So what does that look like? And this is just a little picture from the old book to try to show, graphically, or like a cartoon. So here we have what's the normal enzyme substrate Michaelis complex, A competitive inhibitor is going to bind to the same active site, so therefore the substrate can't get in. So in order for the substrate to get in, you have to add lots and lots and lots of substrate, because then you can compete for binding. Sort of like the Hunger Games of the enzyme world. Pop culture reference. Instead of integration, instead of faith integration. But, all right. Whereas the non-competitive, it's binding someplace else, but it's changed the substrate's active site to where either the substrate doesn't bind, it's no longer catalytically active. It's not competing with the substrate directly, but indirectly. It's no longer catalytically active. And they don't have a picture here of the uncompetitive, which is where it would only recognize this. This one right here, this ES complex. All right, this is from the Leninger book, which isn't quite as cutesy, but it's actually, I think it's more helpful in the sense that mathematically it's a bit more helpful. So here we can see this would be the normal, progression that we've been talking about. And the inhibitor binds the free enzyme. So what it does is it pulls the equilibrium down towards the EI complex. And so it has a dissociation constant, which they call Ki. That's the inhibitor constant. Once again, the lower the Ki, the tighter that inhibitor is going to be binding. And so, yay. So, that being said, that is good. Yeah. So sometimes drugs do this if you're trying to prevent, an enzymatic reaction, because if it can bind, it competes with the substrate. If you get enough substrate around, it can still overwhelm the Ki and go on to form product. This is just, using words of saying the exact same thing. So if you don't like the little cartoony characters, then you can look at it this way. Except it does show you the dissociation constant, which is Ki. They like to use that. It's the same thing as Kd, but specifically the Kd for the inhibitor. And so the way that it affects the Lineweaver-Burke is as follows. You get this, and please don't memorize this right here, but I want you to know how to do Lineweaver-Burke and to know the actual Michaelis-Menten equation, but don't. Your book likes to use the term alpha or alpha prime, which is equal to this 1 plus I over Ki. But this is just to show you that it'll give an apparent different Km over Vmax. Okay, so what we're saying here. So let me make this smaller. We're doing type good. Let me try to draw this. So what this says is that color, whatever that color is, is wild type or no inhibitor. So no inhibitor. Whereas if we have the inhibitor, what it means is if you get to high enough substrate concentrations, you'll reach the same Vmax. So see, Vmax, it goes the same asymptote, but it does affect the apparent Km and Vmax over Km. And so this color, whoops. What? Oh. I know, but it means that iPad got kicked off. Here, let me put plus inhibitor, and then I'll find the iPad. Professor Tesler, I think, is going to help me try to fix that Dear God, have mercy. They're just nuts. All right, so let's see.